Hello everyone, today I will solve the fourth problem related to this chapter, electric field and electric force. And let me write the problem first. So question number 4, we have a charged ring, which has a radius of r, and we would like to find out the electric field from the center of the ring to a point P where the distance is L. So let me draw the figure first. So this is like something that we have. So it's going to be a little bit different perspective because it's, I'm just drawing it like that, right? So from the center of the ring, the point P is located right here. So let me put P here, okay? And again, the radius of this thing is, let's give it a name as small r, okay? And the distance from the center of the ring to here is, let me use another color, is L, okay? And again, the charge of this ring is Q. So the question is, what is the electric field at point P as a function of the radius of this thing and the charge and the distance L? Again, it's obviously a vector, right? It has a direction. Okay, so how are we going to solve this problem? And it's the usual thing. We will take a small part of this thing. We call it infinitesimal part of this ring, right? And then what we're going to do is we will calculate the effect of that infinitesimal charged part of that at this point P. And then we will take all these small parts and add them up using basically, in quotations, continuous summation or integration, right? Okay, so let's do that. So I'm going to divide this ring into small parts, like all of that, right? Like this part, that part. And again, let's say that the charge of this guy is dq, right? And if I take this guy, so it's all, these small parts, right? So what I'm going to do is I'm going to take this guy and that guy, and if I draw the distance between this, so let's see if I can make it exactly. Yeah. Okay. If I look at these two and the others, what I see is the following, right? So the effect of this dq is going to point this way. I hope I'm going to make it point right. And the effect of this one, which is exactly the opposite of that, across that, is this. And the others are going to, this is going to point like that and that. And it's going to make something like a cone, right? Because if you stand at P and if you look at this direction towards the ring, you will see like a cone structure. So that's why the effect of this thing, in terms of the electric field, will also look like a cone, right? And let me extend this up until here. So this angle is theta as well as that angle, right? So when you look at the geometry of this, so if this angle is theta, so is this one and the other one, right? And let me use this in here. So this is also radius r, and this length is L, right? And this distance is, let's call it S, is equal to this, since this is 90 degrees, right? Is L squared plus r squared with the square root, using Pythagorean theorem, right? Okay. Now I'm kind of ready to look at the problem and use the symmetry of the problem to see what the direction is. It's kind of obvious right now, because you see, if I look at the symmetric versions of these, for instance, these guys, the y component of this, let's call it dE, is going to point up and right. And the y component of the one which is at the lower part is going to point down, but the x component will also point right. So as you can see, the y components are going to cancel each other and the x components are going to add up. So if I call it dEy, and this will be like minus dEy, right? It's going to cancel that. And the dEx's are going to add up. So that's why that's going to happen for all these small guys, which are exactly opposite to each other, across each other on this ring, right? So that's why if you start with dq, let me use this one again. the effect of dq is going to be dE, which is normally a vector, right? And it will only be a pure x component because the y components are going to cancel. So it is enough to calculate just the x components, right, for each one of them and just integrate them to get the whole thing. So what is dEx? So this is I hat, which means it's pointing towards plus x direction. So that's I. And what is dx? You can look at the geometry, right? So the x component is the adjacent one, and that's why that's dE magnitude times the cosine of the angle theta, right? So that's dE cosine theta. Okay, therefore, the electric field E is equal to all of these dE guys added up, and that is equal to I times dEx, which is equal to dE magnitude times cosine of the angle, right? Okay, so now we know what to add, which component to add at least. But what is dE magnitude, right? It's very simple, right? dE magnitude is equal to the electric field due to this charge dq. So that's 1 over 4 pi epsilon, the famous factor, right? And then now I'm going to multiply the charge with the, and I'm going to multiply this factor with the charge and divide that to the square of the distance. But I know what the distance is. It's L squared plus R squared, and I'm going to take the square of that. So I'm going to multiply the charge of this object and divide that to the distance square, which is now L squared plus R squared. Okay, and let me even put parentheses here. Now I can just simply put this in here, and then I'll have the magnitude of dE. Okay, and the next thing is this putting this cosine theta here, right? And let's even do that from the geometry. So cosine of theta is equal to, it's the adjacent line, which is equal to L, right? Divided by the hypotenuse, which is L squared R squared with a square root. Okay, so this is the magnitude, sorry. Okay, now I have the magnitude of dE and I have the cosine of the angle theta. So I'm going to put these and put it inside the integral. And, okay, so let's write it down. The electric field is equal to the integral of this thing, which is, and let me put I hat here. We had I hat. Now dE, 1 over 4 pi epsilon 0 dq divided by L squared plus R squared. And I have the cosine theta, which was L divided by L squared plus R squared with a square root, right? And the nice thing about this problem is, compared to the previous one where we had to do some integrals, now you'll see that we don't even have to do any integral. And the reason is the following. Whatever you take, if you take this charge or the other one and other one, all of these charges are located on the ring, and they're both L squared plus R squared away from this point P. So that's why this guy and that guy, as well as this one obviously, this is always the constant, and all of these guys are constant. They can go out of the integral. So that makes the whole question very simple, right? 1 over 4 pi epsilon 0, because they're all exactly the same for each dq that is located on this ring, because R doesn't change and L doesn't change for this, and for any of these, parts of the ring. So that's why they go out of the integral. L is constant, and this is L squared plus R squared, and this is L squared plus R squared with 1/2, right? That's what square root means. If you multiply them, you add the powers. 1 plus 1 over 2 is 3/2, right? So that's L squared plus R squared with 3/2. And inside the integral, the only thing that remains is dq. And that's what I meant by a very simple integration, because we don't even do any integration. If you add all the dq's, that means if you add all the charges, you get q, right? Okay, so here we go. So this is the electric field. E, the electric field, is finally equal to I. That's 1 over 4 pi epsilon 0 q times L divided by L squared plus R squared with 3/2. So this is indeed the expression, the final expression for the electric field. And there's a nice thing about this answer. You can again use this idea, which I really like, the asymptotic limit of all these things, because you should be able to check whether this answer makes sense or not. And the way that we can do is the following. If I take L to be much bigger than R, what does that correspond to? That corresponds to you looking at this ring at a distance which is very, very far away compared to the radius of the ring. And if I do that, then you see that this expression, the denominator, L squared plus R squared, will go to, since L is much bigger than R, L squared, right? If you do that, that's going to be, let me replace this 1 over 4 pi epsilon with K. Okay, it will be I hat K Q times L divided by, now this is going to be L squared with 3 halves. So that cancels that, and you're going to get L cubed, and L cubed cancels one of the L in here, and you get KQ divided by L squared, which is nothing but the electric field due to a single charge with a charge of Q and where the distance is L. This is exactly what we expected, right?